Hello everyone. I welcome you all in today's presentation. For the past few presentations, we are discussing design of various IC engine components such as cylinders, pistons, connecting rods, and crankshafts. And in the last two presentations, we have discussed numerical problems on cylinders, pistons, and connecting rod. In today's presentation, we would like to discuss few numerical problems on crankshaft design so that the students will be familiar with the design process. Before moving further, I would request all the students to please go through the slides of crankshaft design that we have discussed previously so that you all will be in a better position to understand what is actually going on. Just to recall what we have done, the crankshaft are of two types. One is center crankshaft and another is overhung or side crankshaft. In a center crankshaft, there are two crank webs and three bearings, 1, 2 and 3. Whereas in a side or overhung crankshaft, there is only one crank web and two bearings. In this presentation, we would like to discuss problems pertaining to both center crankshaft as well as side crankshaft. So when we talk about the design of crankshaft, what actually we are supposed to do is determining dimensions of this crank pin, that is its length and its diameter, then dimensions of this crank web, that is its thickness and its width, length and diameter of these bearings being 1, 2 and 3, and then the diameter of this shaft which carries a flywheel come belt pulley. So with some alterations here and there, we need to design a center crankshaft as well as a overhung crankshaft, and we have discussed their design procedure in detail in the previous presentations. We all know that a center crankshaft is subjected to bending and torsion movement due to three forces. First is force that is exerted by connecting rod on the crank pin. Second is weight of flywheel acting downwards in vertical direction. And third is resultant belt tensions acting in horizontal directions. Further, irrespective of the type of crankshaft, there can be two positions or two cases. First case is when crank is assumed to be at top dead center and having maximum bending moment and no torsional moment. And second case can be when the crank is at an angle with line of dead center and producing maximum torque. So we need to analyze both the cases. With this background, let us move on to the numerical problems. Here comes first question. In this question, we need to calculate the reactions at the three bearings of a center crankshaft, diameter and length of crank pin, width and thickness of crank web, and total compressive stress induced in the crank web, along with diameter of shaft under flywheel cum belt pulley. And we have been given various datas. So with the background that we have done in our previous presentations of design of center crankshaft, we would like to solve this problem step by step. This is a line diagram of a center crankshaft. So we have been given cylinder diameter as 150 mm, maximum pressure as 4 megapascal. So PP, which is force on the connecting rod, is given by pi by 4 d square into P max, that is 70.6 kilonewtons. Then the weight of flywheel downwards is given to us as 3.5 kilonewtons, and belt tensions in the horizontal direction given to us as 1.8 kilonewton. L by R ratio is 4.75, that is length of rod upon crank radius. Stroke is 200 mm, so crank radius will be half of it, that is 100 mm. Distance between two bearings, main bearings 1 and 2, is given to us as 350 mm, which is B. So we'll assume PP to act in between, so that B1 is equal to B2 equals to B by 2. Similarly, the distance between bearing 2 and bearing 3 is given as 400 mm, and that is denoted by C. So again, assuming that C1 is equal to C2, so C1 equals to C2 equals to C by 2 equals to 200 mm, and maximum bending stress and compressive stress is given to us as 75 megapascals, and tau, permissible shear stress, is 40 megapascals. Maximum bearing pressure is given to us as 10 megapascals, and LC by DC, that is length of crank pin to diameter of crank pin, is given to us as 1. So with the help of the given information, we would like to calculate the desired values. Let's first talk about the bearing reactions. There will be reactions on bearing 1 and 2, that is R1V and R2V, which is due to this load PP, which is supposed to act at the center of the crank pin. Then for this vertical load downwards W, there will be reactions on bearing 2 and bearing 3, and denoted by R2-V and R3-V. Further, for this horizontal component, due to belt tensions P1 plus P2, we'll be having the reactions in horizontal plane, that is R2-H and R3-H. So with this diagram, we'll be able to calculate R1V equals to R2V, which is half of this PP. Similarly, R1-V and R2-V will be half of W, and R1-H and R2-H will be equals to half of the sum of belt tensions. So this is the required reactions at the three bearings. If we need to calculate the resultant reaction, we can do so. Resultant reaction on bearing 1 will be R1V plus R1-V. This is the vertical plane, and R1-H in horizontal plane. So if we square this R1V plus R1-V, and if we add R1-H square and take the root of all the two reactions, then we'll be getting the resultant reaction in on bearing 1. Similarly, we can do for bearing 2 and bearing 3 also. Next step, we need to find the diameter and length of crank pin. We have discussed this, that the central plane of crank pin is subjected to a bending moment, and the bending moment at the central plane is given by this reaction R1V into distance B1. So we have calculated this. Similarly, we have been given bending moment is equal to sigma B over pi d c cube upon 32, that is Z and sigma B. So putting the values of sigma B and MBC, we get DC cube as 840 into 10 to the power 3, or DC as 95 mm. Since LC by DC is given to us, which is 1, so LC will be equal to DC equals to 95 mm. Further, we need to check whether the dimensions that we have obtained for length and diameter of crank pin, they are okay from the point of view of bearing pressure. So what we have done, we have calculated the bearing pressure, which is load over projected area. So bearing pressure comes out to be 7.83 megapascal, which is less than the permissible maximum bearing pressure given as 10 megapascal. So our design is safe from the point of view of maximum bearing pressure. So our LC and DC will be equal to 95 mm for the given dimensions. Next, we need to find width and thickness of crank web. What we'll do, we'll assume empirical values of thickness and width of crank web, which is given by 0.7 DC and 1.14 DC. These assumptions are duly mentioned in the data book, so we can very well refer the data book for the same. And our strategy will be to check for the induced stresses, and if the induced stresses are within the permissible limits for these values, then we can presume our design to be safe. So we know that left hand crank web is subjected to eccentric load R1V. You can see over here, this is eccentric load R1V, and we need to design this crank web. So to understand the effect of R1V on this crank web, what we have done, we have assumed two equal and opposite forces equal to R1V at the center of this crank web. So this force, this downward force R1V will definitely induce compressive stresses, and this load along with this load will create a couple which tend to bend it. So the direct compressive stress is given by the load R1V over area, which is width and thickness of crank web. Since we already found width and thickness, we can obtain the value of sigma C as 4.9 megapascal. Further, the bending moment at the central plane will be given by R1V is the load. We need to find this distance from this load to this mid plane of crank web. So total distance is V1. We'll reduce LC by 2 from this, and further T by 2 from this. So the distance will be B1 minus LC by 2 minus T by 2. We know all the values. We have already found what is R1V, B1, LC and T we know. So we'll find sigma B, and Z will be 1 by 6 WT square. So sigma B comes out to be 36.39 megapascal. This is bending stress, this is compressive stress. The total compressive stress is 4.59 plus 36.39, that is 40.98, which is less than the given value of bending stress or compressive stress, that is 75 megapascal. Hence we can presume that the dimensions of crank web, that is thickness and width, that we have presumed are safe. Now we also need to find the diameter of shaft under flywheel. So we know that this shaft is subjected to bending moment in the horizontal plane and in the vertical plane. So bending moment in the vertical plane is MBV equals to R3 dash V into resistance C2. Similarly, bending moment in the horizontal plane is R3-H, which is this load, into C2. So, since we know R3-V and R3-H and C2, we can find these values. Resultant bending moment will be given by this equation. So, we got this resultant bending moment, and since MB is pi ds cube upon 32 into sigma b, where ds is the shaft diameter under flywheel, we can find value of ds as 40 millimeters. So we saw that For a center crankshaft, for a case when crank is at top dead center, we found various dimensions such as length and diameter of crank pin, dimensions of crank web, and the diameter of shaft under flywheel. Let us move on to next question. This question pertains to design of a side crankshaft. First of all, let us see what this 500 mm into 600 mm means. Whenever we are encountered with such a designation, we need to be sure that what information does this provides. So in this case, 500 mm will always be the diameter of bore and 600 mm will always be the length of stroke. So D will be 500 mm and length of stroke will be 600 mm. Further, we have been given weight of flywheel as 80 kilonewtons and extrusion pressure is 2.5 megapascal. A point worth mentioning is this 2.5 megapascal will be used to calculate the force PP for case 1 when crank is assumed to be at top dead center. In this question, we are supposed to analyze the side crankshaft for case 2, that is when the gas pressure at maximum torque is 0.9 megapascal, the crank angle is 30 degrees. So analysis will be a bit more involved, and we have been further given the connecting rod is 4.5 times the crank radius. That means the ratio L by R is 4.5, and any other data will be suitably assumed. So this question will be very helpful in developing an understanding of the design of side crankshaft questions and what data we need to assume when they are not given in the question. So these are the data that is given in the question. Now let us see which data is not given and how we'll assume that data. First of all, we need to analyze it for the case in which torque is maximum at a particular angle, that is 30 degrees in this case. So for this case and this pressure, that is 0.9 megapascal, we'll calculate the force acting on piston due to gas pressure. Comes out to be 176.7 kilonewton. Now the thrust on connecting rod is denoted by PQ, which is this. It will have two components, tangential component PT and radial component PR. For theta 30 degrees, we need to find what is phi. So this triangle will give us the relation sin phi is sin theta upon L by R. L by R is known to us. Theta is given to us as 30 degrees. So we'll be able to find what is phi, which is 6.37 degrees for this case. Now we can very well find this PQ, which is PP upon cos phi, and PT and PR from these relations. So we are able to find PQ, PT and PR. These forces will be required to find reactions and in finding other dimensions. Now we need to find the dimensions of crank pin. Since a lot of dimensions are missing, so let us find length and diameter of crank pin considering crank pin at top dead center so that unknown dimensions can be represented in terms of length and diameter of crank pin. So this PP will be the force on connecting rod assuming maximum pressure, that is given by PB into LC into DC, length of crank pin, diameter of crank pin. PP we have already calculated for the given maximum pressure. The text that is written in red font, it is the values that we've assumed, and data book will be very helpful in assuming these values. So assuming LC by DC, as 1 and maximum permissible bearing pressure as 10 megapascal. We have taken these values from data book of V. Bhandari from page number 29.45. Since ratio is known and PB is known, we'll be able to convert this equation into one unknown, that is DC. So DC we calculate as 221 mm, or raising it to next higher number, let us say 230 mm. Since LC by DC is 1, so length of crank pin will also be 230 mm. Now length of bearing 1, which is this L1, it is 1.5 times DC. These relations are given in the data book, and those will be very helpful in case we are supposed to assume data. So it comes out to be 345 mm. For the thickness of web is 0.5 DC. This relation is also given. So 115 mm. Since B and C are not given to us, B is the distance from bearing 1 to this force PR. So B will be, we will assume that this force will act at a distance of 0.75 LC. So 0.75 LC plus thickness of web plus 0.5 of L1, which is length of bearing 1. So this comes out to be 460 mm. Similarly, C is the distance between bearing 1 and bearing 2. So C will be 0.5 of L1 for this bearing and 0.5 of L1 for bearing 2, followed by width of flywheel, which is not given to us, and some margin. So assuming width of flywheel as 200 mm and putting the values of L1 and assuming margin as 15 mm, C comes out to be 560 mm. Further, we'll presume C1 equals to C2 equals to C by 2 for this case. So this slide will give us idea about dimensions that we are required to assume from the relations given in the data book, and that is also necessary to find the dimensions of crank pin, then crank web, then shaft under flywheel. Now, since we have found the LC and DC from the bearing pressure considerations, but we are supposed to find it for the crank when it is at an angle of 30 degrees. So what we'll do, we'll take those dimensions and then we'll try to find the induced stresses. If the induced stress is less than the permissible stress, our dimensions that we have calculated from the bearing pressure point of view will be safe. So we have checked for the induced stresses in crank pin. PR and PT will act at a distance of 0.75 LC that we have already discussed in the lecture slides. Now, bending moment in vertical plane will be given by PR, this load, into this distance 0.75 LC, plus bending moment in horizontal plane is PT, this distance, into this force into this distance. Since we know PR and PT and we know LC, we have calculated the load. So the bending moment, the resultant bending moment comes out to be this 30664 kilonewton millimeter. Section modulus of crank pin is pi DC cube by 32. Since we have already calculated DC, that is 95 mm, so we'll be able to find Z. MB is known to us, Z is known to us. We can calculate sigma B, which is 25.68 megapascal. Since this sigma B is less than the permissible value, that is 75 megapascal, our design is safe. So whatever dimensions we have calculated from the bearing pressure consideration, those dimensions are safe when the crank pin is subjected to the forces PR and PT. Position to find bearing reactions. This is the vertical loading diagram. PR is supposed to act at a distance of 0.75 LC from bearing 1, from crank web, sorry, and in this we need to find R1V and R2V due to this load PR, and R1-V and R2-V due to the weight of flywheel. So using simple moment equations, we'll be able to find these four reactions. The horizontal loading diagram. Here, that P1 plus P2, which is sum of well tensions, is not given. So we'll assume this value as 0. So we'll be having reactions in horizontal plane due to this PT force as R1H and R2H, but R1-H and R2-H will be equal to 0 since P1 plus P2 equals to 0. So using simple equations of taking moment about the bearing 1 and 2, we'll be able to find the reactions on bearing 1 and bearing 2, and then we can find resultant reactions also. Now let us come to the design of crank web. We know that a crank web is subjected to following stresses. First is bending stress in horizontal plane and vertical plane due to force components PR and PT. Then direct compressive stresses due to radial component PR and torsional shear stress due to tensile component PT. Again, we'll follow the same strategy. We'll assume the web thickness, web width in the form of DC, that is die of crank pin, and we'll take diameter of bearing 1 as equal to L1, length of bearing. So L1 by D1 is 345 mm. And then what we'll do, we'll check for induced stresses. If the stresses are coming within the permissible limits, our dimensions are safe. So what we have done, we found bending moment due to radial component. MBR is PR into this distance 0.75 LC, plus since we are presuming it in the central plane, so T by 2. Similarly, Z is 1 by 6 WT square. So sigma BR comes out to be 32.5 megapascal. Further, bending moment due to tensile component is MBT is PT. This PT into R minus D1 by 2. D1 is diameter of bearing 1. Sigma BT is again MBT by Z. So putting all the values, it comes out to be 13.26 megapascals. And the direct compressive stress due to real component is PR upon W into T, which is 2.75 megapascal. If we sum all the three stresses, the maximum compressive stress is 48.45 megapascal. Now we'll find the torsional moment on the arm, which is given by PT 0.75 LC plus 0.5 T. Since tau is T by Z and Z, which is polar section modulus for the crank web, is given by WT square upon 4.5. So the stress comes out to be 17.93 megapascal. Now using the maximum normalcy theory, we'll calculate sigma C max, which is given by this equation. For safe design, it should be less than sigma C permissible. So sigma C max comes out to be 54.34 megapascal, and if we assume the maximum compressive stress as 60 megapascal for the material of crank web, our design comes out to be safe. Now we have already decided the length and diameter of bearing 1. So let us check the same for the bearing pressure. Bearing 1 is subject to resultant reaction at bearing 1 upon diameter and length, which is projected area of the bearing. So what we have done, we have found the resultant reaction at bearing 1, which is given by R1V plus R1-V whole square plus R1-H whole square, comes out to be 356.76 kilonewton. Putting the value of R1 and D1 L1 we have already found, PV comes out to be 2.99 megapascal. If we assume the safe value as 10 megapascal, it is well within the limits. So our design is safe. Further, we'll make bearing 1 and 2 as identical. Next, we need to find the shaft dia under flywheel. We know that central plane of shaft under the flywheel is related to maximum bending moment, and the bending moment is given by MBV PP B plus C1. This B plus C1 minus R1V plus R1 dash V into C1, and MBH is given by R1 dash H into C1. What we'll do, we'll find the shaft diameter for the case when crank is at top dead center, that is assuming a single load PP at the crank pin, and then we'll check this for the induced stresses for the given case, that is when crank is at an angle of 30 degrees. So with these data we found the diameter of shaft as 335.9 or say 340 mm. Now we need to check whether this shaft diameter of flywheel shaft will have safe stresses for the case of crank at some angle. So what we have done in this given case, now the central plane of the shaft will be subjected to bending moment in horizontal as well as vertical plane, and then torsional moment due to PT force. Again, using simple equations, we found bending moment in vertical plane, bending moment in horizontal plane, then resultant bending moment, then torque, then we have calculated resultant shear stress using maximum shear stress theory. It comes out to be 5.8 megapascal for the shaft dia of 340 mm. So since induced shear stress is in the shaft is very low, so we can say that our shaft design is safe. So flywheel shaft diameter ds will be 340 mm. So let us summarize the results that we have obtained. From the analysis, we have obtained DC as 230 mm, LC as again 230 mm, length of bearing 1 345 mm, diameter of bearing 1 345 mm, bearing 1 and 2 will be made identical, thickness of web 115 mm, width of web 460 mm, dia of flywheel as 340 mm. So these were the two questions on the design of center crankshaft and overhung crankshaft. This is another question that has also came in the RTU examinations held in 2018-19. If we have understood the design process that we have used in the previous two questions, it won't be difficult to solve this question, and I would like that the students should solve these questions by themselves. What we'll do over here is we'll discuss the design steps, so that following the design steps you'll be able to solve these questions without much difficulty. So in this question, we have been given bore dia, stroke length, engine speed, mean effective pressure, maximum compression pressure, weight of flywheel, total belt pull, and the case is case 2 when crank has turned through 35 degrees from TDC, and pressure on that point of time is 1 megapascal when torque on the crank is maximum. Further, L by R is also given to us as 5, and we have to assume, like the question number 2, any other data which is not given. So you might see that we have not been given the distance between the bearings, bearing 1 and 2 and bearing 2 and 3. So we need to find the distance so that it is possible for us to find the reactions. So let us see the design process in steps. What we'll do in step 1, we'll assume the crank to be at TDC like we have done in the previous question, and we'll calculate maximum force PP on the crank pin, and assuming LC by DC ratio and bearing pressure from the data book and we'll find length and diameter of crank pin exactly in the way in which we have done in numerical number 2. We'll assume various dimensions such as distance between bearing 1 and 2, that is B, distance between bearing 2 and 3, that is C, width and thickness of web from the empirical relations given in the data book in terms of LC and DC. In step 3, what we'll do, for the given angle 35 degree, we'll calculate phi, and for the given value of L by R, for bore diameter of 400 mm and pressure 1 megapascal, we'll calculate PP and thereby PQ, PR and PT. And for this crank position and calculated value of LC and DC, we'll check for the stresses induced in the crank pin. If the stresses induced are within permissible limits, the design of crank pin is safe. In step 4, we'll calculate horizontal and vertical reactions on all the 3 bearings due to tangential force, radial force, weight of flywheel and horizontal valve pull, and find resultant reactions on all the bearings. The assumed value of width and thickness of crank web, calculate induced stresses in the crank web. In step 5, for the assumed value of width and thickness of crank web, we'll calculate induced stresses in crank web for the crank position at theta equals to 35 degrees. Stresses would be within permissible limits. If they are not within limits, we can increase width of the crank web. In step 6, we'll determine diameter of shaft under flywheel for the crank position at TDC and check for induced stresses. Exactly what we have done in the second question, we need to do over here also. And the stresses induced should be less than the permissible stresses. Permissible bending in compressive stresses can be assumed as 75 megapascals and shear stress as 40 megapascals, as the same is not given in the question. And then in the end, we'll list all the parameters such as length and diameter of crank pin, width and thickness of crank web, length and diameter of bearing, and diameter of shaft under flywheel. So with this, I would like to conclude. It seems that the analysis of crankshaft is too lengthy and it will not be possible to solve the numericals in the examination within the stipulated time. But in my opinion, the analysis may look cumbersome and lengthy, but definitely it is doable. Moreover, you will be having a great help in the form of data book in assuming data that is not given in the questions. So, once we are familiar with the design procedure, we will definitely be through, and that too with flying colors. I hope that this presentation will serve as a preliminary step in making you comfortable with the numerical problems on crankshaft design, and you will be able to solve many more problems of crankshaft design. Thank you all for your patient hearing.